Greetings everyone, dear 13th IST conference participants. I'm Nenad Petrovic, a PhD student and teaching assistant at Faculty of Electronic Engineering, University of Niš in Serbia, Department of Computer Science. In what follows, I'll present you my paper entitled Prototyping PIC16-based COVID-19 Indoor Safety Solutions within Microcomputers Systems course. All of us are witnessing that current COVID-19 pandemic dramatically affects almost any aspect of our everyday lives. Education is one of them as well. Switching to distance learning has caused many issues related to teaching process and methodology. Laboratory sessions are a constituent part of many study programs and courses. They often require specific equipment and interaction between students and teachers as well. Two aspects will be considered in this paper. The first one is how the laboratory sessions of Microcomputer Systems course held on third year of Bachelor degree of Computer Science at our university were actually adapted for distance learning scenario during the pandemic, which are the outcomes of these changes, benefits and opportunities. On the other side, it will be considered how practical exercises related to current COVID-19 pandemic can actually motivate students during the course. For about 2 decades, the laboratory sessions were held in groups of 20 students doing exercises related to PIC16 microcontrollers. They had homework assignments, which later had to be extended by teachers' requirements during the laboratory session. The codes were executed later on EasyPIC7 development board. We had around 4 boards available. Teacher asks finally some basic questions related to the current topic before checking the assignment code and asking some more questions about the code itself. However, during the pandemic, we had to switch to remote sessions, so we introduced several novelties. Proteus simulation environment was used instead of physical boards, and students had online tests instead of questions directly asked by the teacher. PIC is a microcontroller family introduced by microchip technology back then in 1976, with the first model PIC1650. After more than 40 years, these microcontrollers are still quite popular due to their affordability and fantastic support by both manufacturers and community. In our course, the main microcontroller which is studied is PIC16-F84A. Moreover, in this paper, one more microcontroller from PIC16 family is also introduced due to additional capabilities such as analog to digital conversion and one more port available. On the other side, Proteus Design Suite is a proprietary software package which enables virtual system modeling and circuit simulation that covers the needs of our course. Now, let's take a look at the COVID-19 indoor safety system based on PIC16 microcontrollers, which represents a typical exercise. In what follows, the 3 main components will be described, while the 4th is outside the scope of this course. The main control unit consists of PIC16-F84A microcontroller executing assembly code. In case one new person arrives, RB0 interrupt is triggered. If person wears mask and has temperature which is less than 37 Celsius degrees, then in that case the door will be opened. In our simulation, actually green LED will be turned on. Otherwise, the door will be closed and the red light turned on. On the right hand side, you can see the assembly code. The second part of the system is passenger detection based on ultrasonic sensor. For that purpose, a distinct unit of the same microcontroller model is used, executing code written in C programming language and equipped with SRF04 ultrasonic sensor. The distance measurement method is described on this slide. If the measured distance between the sensor and the person is below the given distance threshold, then it will be checked whether the number of persons inside the building is below the number of maximum persons allowed. If that is fulfilled, then signal 1 will be sent via RA0 pin to the control unit. Otherwise, it will wait for RB0 high signal, which is actually sent when one person leaves the building. Moreover, this unit shows the number of persons inside the building using the 7-segment display. Finally, the third part of the system responsible for temperature measurement is based on PIC16F870 and equipped with LM35 analog temperature sensor, which is connected via RA0 pin operating in analog to digital conversion mode. The code was written in C programming language and measurement method shown on this slide. If person's temperature is greater than 37 Celsius degrees, then high signal will be sent via RC3 pin to the control unit. Otherwise, signal 0 will be sent. Now, we'll take a quick look at live demo within the Proteus simulation environment. On left side, I can set the temperature of the person which passes the entrance of the building, which is currently set at 36. On the other side, I can set the distance between the person and the ultrasonic measurement sensor, which is currently 7. The threshold for this value is 8, as we can see from the code right here. On the other side, the threshold for temperature is given here, and it's 37. Now, if I run the system, the LED light will be green. If I increase the temperature, it will be red. The display shows the number of persons currently inside the building. If I increase the distance, new persons aren't detected anymore. If we decrease the temperature and simulate that person doesn't wear a mask, the light becomes red. When it comes to evaluation, two distinct aspects were considered. The first one is system performance, expressed as distance accuracy, which was 1 centimeter, and temperature precision, which was 0.1 Celsius degrees. On the other side, indicational impact was also analyzed. The percentage of students involved into laboratory sessions was increased compared to previous years, and on the other side, their average grade was also higher, which confirms the effectiveness of the approach. It can be concluded that the proposed method has shown better results when it comes to both student engagement and average laboratory session grade. It can be explained by the fact that in past, due to limited number of development boards for laboratory sessions, the students were not able to completely experiment and execute with their codes. In future, we also plan to adopt the similar approach with Proteus-based simulation environment for our future Internet of Things course, which will be available as elective for students enrolled on the new bachelor degree accreditation. We also plan to extend the course's topics with Raspberry Pi, Arduino, and ARM-based microcontrollers. This work has been supported by the Ministry of Education, Science and Technological Development of the Republic of Serbia.